Hello everyone. So today we are going to discuss about the effect of frequency offset in OFDM. In the earlier class, we understood the concept of OFDM. We also understood that all the subcarriers are orthogonal, and we also discussed about the cyclic prefix, and by adding cyclic prefix we were able to make parallel channels which were of flat fading in nature. So now today we will discuss if there is a carrier offset, then what happens in the OFDM signal to noise ratio. So basically, if there is a frequency offset in OFDM, then you may lose orthogonality. Of the subcarriers. This will introduce interference, and which is going to affect your signal to interference noise ratio SNR. This will go down. In RF, what happens when the user is moving towards a receiver or away from the receiver? There is change in the carrier frequency, which is called as Doppler shift. And the second possibility could be that the local oscillator at the receiver might drift. So in both the cases, the orthogonality of the subcarriers is lost. The moving of user is not an issue in indoor optical wireless communication system. So basically the offset may occur because of offset in the local oscillator frequency at the receiver. So let us try to calculate what will be the signal to noise ratio when there is a frequency offset. So for that we need to define a parameter which is called as normalized frequency offset. So let us define this as, this is delta F is the frequency offset, and B, as we know, is the bandwidth, and N is the number of subcarriers. So I'm defining a parameter epsilon, which is normalized frequency offset. Normalized frequency offset, which is defined as the delta F, that is the frequency offset, divided by the spacing between the two subcarriers, which is B by N. B is the total bandwidth and N is the number of subcarriers. So let us consider this particular equation. This is the received signal or received sample, received sample, and N is, as I told you, is the number of subcarriers, and xk is the data on the kth subcarrier, data on kth subcarrier, and hk is the corresponding channel coefficient, as we had discussed that the OFDM makes the channel as frequency fading channels. So you have basically parallel channels for each subcarriers defined by, for example, this is first carrier H1 and xk is the data reading on it. So there are k such channels, and this will be e raised to j 2 pi n k plus sigma. Sigma epsilon is the normalized frequency offset. Let us consider this now. And this is the noise. Now yn is given by 1 by n. Now let us try to understand this particular equation. This is equation 1. When epsilon is 0, there is no frequency offset. Whether does it lead to situation when the channel becomes a flat fading channel. So let us put epsilon is equal to 0. So this gets reduced to 1 by n summation over all the subcarriers xk, hk, e raised to power j 2 pi n k by n, whereas epsilon is 0 plus the noise. And if I want to extract the data on the lth subscriber, this is lth data on lth subcarrier, receive data on the LS subcarrier is given by 1 by n yn into e raised to power minus j 2 pi n L divided by n. This we have studied when we were discussing about OFDM. So let us now put the value of y1 from this equation in this equation of YL, capital YL. So by putting this yn from this equation number 2 into equation for capital YL, so this becomes 1 by n, the two summations n and summation of subcarriers, and this is xk into e raised to j 2 pi n k by n into e minus j 2 pi n L by n plus this is the noise term. So this is actually 1, or not 1, but this will give me, this is only valid when n is equal to L. So this will give me WL, and so I am left with this expression plus WL. And now let us break this whole thing into two parts. One is when k is equal to L, which will give me this XL into HL, and k not equal to L. So this is k not equal to L. So I have broken this into two parts, k is equal to L and k not equal to L. So this particular thing is 0 because of orthogonality condition. So I am left with XL into HL plus WL. So the final expression becomes XL, that is the data on LS subscriber, the channel coefficient for corresponding to the LS subscriber plus the noise in the LS subcarrier. So this, we already had seen this result when we had a frequency selective channel, and then we, using OFDM, we made it flat fading channels, and these are the subcarriers, and they have channel coefficient as H1 or 2HN, and each has data. This is X1, this is XL. So we get back the same result as discussed earlier. Now go back to the same equation and let us now understand the effect in the presence of frequency offset. So the yn, the received sample, is given by, in the presence of frequency offset, this epsilon is frequency, normalized frequency offset. So we have seen this when epsilon is 0, and we got back our, as we had discussed in the OFDM lecture. So this is in the presence of frequency, normalized frequency offset. And so YL, the data on the LH subcarrier, can be written as 1 by n, yn received signal e raised to minus j 2 pi n L. Now putting this yn here, will give me this equation. So I'm simply putting YL here and doing some mathematical adjustment here. So this is what I get. So there are two terms here. Now, in order to solve this particular thing, we will take certain approximations and see what kind of results we get. So in order to solve this equation, let me name this as A. I will use some approximations. So first approximation is, or the first identity I will use is summation n is equal to 0 to n minus 1. A e raised by j theta n is actually equal to sine n theta by 2 divided by sine theta by 2. So using this identity and putting in the equation which I had named as A, in this equation A, replacing actually e raised by j theta here, I get HL XL sine pi epsilon divided by sine pi epsilon divided by n into 1 by, this is into 1 by n plus summation. And again, here also I have changed using this equation. And this is the noise part, the WL. Now, in order to calculate signal to interference noise ratio, we need to calculate signal power. So signal power is, in the last equation, if you see here, this is the desired signal or signal power, and this is the interference part. And this is the noise part. So let us try to calculate the signal power. So signal power is given by expected value of HL mod of HL square into expected value of EXL, because HL and XL, they are independent, into sine pi epsilon divided by n pi epsilon by n whole squared. So this is the signal power coming from the equation A, the signal part. And we can approximate this value, sine pi epsilon divided by n pi epsilon by n. So sine limit sine pi epsilon n is actually equal to pi epsilon divided by n when, you know, this factor is small. Pi epsilon into n is small. So this is true when, which actually is small because there will not be a major frequency offset, is small. So this identity is valid if this pi epsilon divided by n is small. So this will give me, I multiply by n both sides. So this n sine, that is this part, is nothing but equal to pi epsilon. So my signal power, replacing this part by pi epsilon, I get expected value of HL square into P. P is the power in the data, that is expected value of XL mod XL whole square is the power in the data. This is power in the data symbol, multiplied by sine pi epsilon divided by epsilon whole square after considering this approximation. So this will give me P. If I take the average value of channel coefficient as H, then I get signal power as P, there's power in the symbol, into average value of the channel coefficient into pi epsilon divided by pi epsilon whole square. So this is the signal power we have got. Now let us try to calculate the interference power, and then we will be able to calculate the signal to interference noise ratio. So interference power taken from the earlier equation from this part. So I'm now trying to calculate this part. This is the interference part. Is given by expected value of IL mod of IL square into expected value of channel coefficient into the expected value of mod XL square multiplied by summation sine pi epsilon n sine divided by n sine pi L minus k plus epsilon into n whole square. And this is term actually is for k not equal to L. K is equal to L was the first signal part. So this is the interference part. So let us do a substitution here. Put L minus k is equal to U. And we can also take an assumption that U plus epsilon is U because epsilon is very small and N is very high. So under these conditions, U plus epsilon is equal to U because epsilon is high and N is high, number of subcarriers are high. Under this condition, expected value of IL square, there is the interference part is P. P is again the power in the data symbol. H is the average channel coefficient. And these limits on the summation, they change. They become U is equal to minus infinity to infinity. And because your N is tending to infinity, and then you have the bracket sine pi epsilon and sine pi. L minus k I have replaced by U, and U plus sigma is U. This is approximation I have done. And this is U not equal to 0 because L is not equal to k. So both are same. So with this equation, what we get is P into H mod square, and I take sine pi sigma square outside. This is summation, this is over U minus infinity to infinity, 1 by n sine pi U by n whole square. Now let us try to find a bounded solution to this problem, and we know that sine theta is always greater than 2 theta by pi. So I'm just trying to find the bounded solution for this interference equation. So assuming sine theta is equal to 2 theta by pi, so I replace this sine pi U by n using this expression. And then by doing this, sine pi U by n will be greater than 2 pi U divided by n divided by pi, which is 2U by n. So which means n sine pi U, the whole expression here, is greater than 2U. So using this approximation and finding out the bounded solution, what I get is expected value of the interference component, interference power is less than or equal to P H square into sine pi epsilon whole square, and then we have this summation, and U is not equal to 0. So I can take this 2 outside, and then there is a standard expression for summation minus infinity to infinity of 1 by U whole square, which is nothing but pi square by 6. So this is, and I can also replace, this is twice because this is symmetrical. So this is twice of U is equal to 1 to infinity. The limits I have changed. So this is twice of this infinity U is equal to 1, and some expression is actually equal to U is equal to minus infinity to infinity, this expression. So using this, I get a simplified expression 1 by 2 P into mod H square sine pi epsilon whole square summation U is equal to 1 to infinity 1 by U, and this is a standard identity, and this gives a value pi square by 6. So putting this value, the total expression becomes pi square by 12 power in the data symbol, the channel coefficient, average value of the channel coefficient for different subcarriers, into sin square pi epsilon. So this can be further simplified, and it is 0.822 p s square sin square pi epsilon. So now we have calculated the value of interference power. Now we are in a position to calculate the signal to interference noise ratio. So this was the signal part which we had calculated earlier, and this is the interference part which has come from this particular equation, and this is the noise part. So under the presence of frequency offset, which we had defined through a parameter epsilon, normalized frequency offset, our SNR is given by this equation. Now let us try to understand the effect of this frequency offset on the SINR. How much is the degradation which is caused because of this frequency offset? So let us understand this using one example. So let us assume that average channel coefficient is 1. The data power, which is actually P, is say 10 dB, and assume the noise is 0 dB. Because we want to see the effect of epsilon, so I am making some simplified assumptions here. So let us find out what is the value of SNR when there is no interference, and what is the value of SINR when there is interference. And we will calculate SNR for with and without carrier offset, that is either sigma is equal to 0 or sigma has some value. Epsilon has some value. So in this example, let us keep this epsilon as 5% or 0.05. So for these values, let us try to calculate the SINR using the earlier formula which I had derived. So this is given by this signal power part, signal power. This is the interference, just putting the values here. And of course, the noise was 0 dB or 1. So this was the noise. So this gives me 5.25 dB as the SINR. Now, let us calculate the SNR. SNR meaning there is no interference, that means there is no offset. The epsilon is 0. So if I keep epsilon is equal to 0 here, what I get is SNR. So this will be P s square. This limit will actually tend to 1. So this will be 1 divided by this term, the interference part will be 0. So 0 plus sigma n square. So this is what I get as the SNR. And putting the values of P, H and noise, we get SNR as 10 dB. So notice here that because of the frequency offset, the SNR has fallen to by approximately 5 dB. It has become 5.25 dB. So that's the effect frequency offset will have in OFDM transmission. Further, just to find out what is this delta F frequency offset. So epsilon is, this is how we are defined delta, so as epsilon is equal to delta F divided by B by N. So I'm trying to calculate delta F from here. So delta F will give me epsilon B by N, and this is 0.05 into B, let us assume it as 4 megahertz, and number of subcarriers, say I take example 256. So this will give me 15.625, this particular thing, and multiply by this will gives me a delta F of 0.78 kilohertz. So that's the frequency offset. And now let us understand this offset as a fraction of carrier frequency, and I'm assuming that the OFDM is being transmitted at say 2.4 gigahertz. That's the carrier frequency. So if I see the fraction of carrier frequency offset, it becomes 0.78 kilohertz divided by 2.4 gigahertz. So this gives me 0.33 ppm. ppm stands for parts per million. That is 1 in 10 to the minus 6 is 1 ppm. So what I get is 0.33 ppm. So that is the offset which will give a degradation of SNR by almost 5 dB for these parameters. So maintaining the local oscillator frequency and containing the offset is very, very important in OFDM. It's very challenging in cellular or RF communication, but that is not the case here because in our optical wireless or indoor communication, the user is not moving. So only issue will come from drift in the local oscillator at the receiver. So that we need to maintain exactly at that value. Otherwise, any slight offset as low as 5% or 0.05 will degrade the SNR performance. So this is the effect of frequency offset on OFDM. Now let us try to understand another issue which is there in OFDM, which is called as PAPR, which stands for peak to average power ratio. This is very important in OFDM because OFDM signal has high PAPR, and we know that in optical wireless communication system we normally use LED or laser, and if you see their characteristic, that is this is a voltage or I given to the device, and this is the say power output P. Then for LED it is linear and it has some dynamic range. After that it sort of saturates, and for laser also it is linear. So both the devices, they have some limited dynamic range. The laser is actually a little different, where you have it's a threshold device, so then sort of saturates. So it has limitation, and if the OFDM signal, the voltage level of the OFDM output is higher than the dynamic range of these devices, then it results into distortion. So we need to contain this peak to average power ratio. So it is very, very important when you are designing a OFDM system to contain the PAPR value. So let us now try to understand this peak to average power ratio for OFDM. Before that, let us understand for a single carrier, what is PAPR. That will explain the definition of PAPR. So for example, for single carrier system, say, and I am using, for example, BPSK, then the data will be x0, for example, x1, x2, so on and so forth, xn. And this can have value either a or minus a, depending upon the constellation. So this is, for example, this is 0, this is a, and this is minus a. So this can have a, this can have minus a or whatever. So if you see the power in each symbol, is A square. A is the amplitude, the power in each symbol is A square. And if I calculate the average power, because this is peak to average power, so this is the peak power in each symbol. So average power will be expected value of xk whole square. So from these, for a BPSK signal, so this will be is going to be A square only. So if I calculate the peak to average power ratio, that is PAPR, it will be A square divided by A square. This is the peak power, and this is the average power, which is 1, or you can say it is 0 dB. So this is a case of single carrier system using BPSK constellation scheme. Now let us try to understand the PAPR in OFDM. So OFDM signal, if you recall from our OFDM discussions, so I'm not drawing the total OFDM block diagram, just drawing the IFFT part. So where you have, these are the data symbols or the constellation. So this is x and minus 1, and this is in the frequency domain, and then IFFT converts into time domain, which are, these are the samples. So these are the samples, x0 to xn minus 1, where n is the number of subcarriers. Now the xk, the sample, is given by 1 by n summation I is equal to 0 n minus 1 data on the xi into e raised to power j 2 pi ki divided by n. Average power for these sample, which are x0 to xn minus 1, is given by expected value of mod value of sk square. Now let us put this value of sk here and try to evaluate this average power. So this will become 1 by n square, just putting the value of xk here and squaring it, 1 by n square summation, and then this becomes power xi, mod value of xi square and expected value of this. And this is 1. This is equal to 1. So I'm reduced to 1 by n square summation over all the subcarriers, expected value of xi mod square. And this value, expected value of xi, because samples at the output are changing, so I'm assuming it to be A. So I'm just trying to find out the maximum average power. So this will give me 1 by n square summation A square, and then doing summation for all the subcarriers will give you A square plus A square plus A square n times. So the total A square into n divided by n square, which is nothing but A square by n. So this is the average power, which is given by A square by n. Now let us try to calculate the peak power. So the peak power is given by mod value of xk, that is a sample given by this equation, and so this 1 by n can be taken out. Then we have xi into e raised to j 2 pi ki by n, and this will give me this is 1, So this is equal to 1. So this 1 by n into summation I is equal to 0 and minus 1 into a, and this is a plus a n times, na divided by n gives me a. So this is the mod value of the sample here. And if you take the power, this will be a square, the power. So if I calculate the peak power we had calculated just now as a square, and the average power I had calculated in the last slide, this was the average power, a square by n. So basically it gives you n. So higher the number of subcarriers, higher is the PAPR. Higher numbers of subcarriers will result in high PAPR. This may not be as high as n because we have taken some, because sample amplitude is changing, so the average value will change to some extent. So this will be little less than this. So this is the PAPR for OFDM, and this is how it is defined in practice about the PAPR. So normally one one uses CCDF, that is complementary cumulative distribution function, because this is not constant, so distribution function, CCDF. So if you plot, say this is PAPR value, and this is your, say, the probability that x is greater than x, that is the value of PAPR is greater than some threshold, that probability, which is defined by this complementary cumulative distribution function, which is can be written as fx x, and this is the PAPR. So the curve will be something like this. So this is the result you will get for PAPR measurements. So this is a starting from 0 to 1, this is a 0.8, and this could be, for example, 10 dB, this is say 4 dB, and these are say 15 dB. I'm just putting some approximate values. So when the PAPR threshold is considered as 10 dB, then the 20% of the signals or 0.2 of the signals will be more than 10 dB. Otherwise, 80% or 0.8 part signal will have PAPR less than 10. Different data symbols will have PAPR less than 10 dB. So the correct definition, or the way it is defined for OFDM, is to find out the CCDF for PAPR. So basically it tells you what is the probability that the value is more than certain threshold, right? So higher the PAPR, there will be more degradation in the performance of the system, because the devices which are being used, they have limited dynamic range. So if they exceed the dynamic range, the signal, OFDM signal exceeds the dynamic range, then it results into distortion. So this was about PAPR, and there are a lot of techniques which have been explored for the reduction of PAPR. So we will not go into the details of these techniques, but some of these techniques, like clipping technique, you clip the signals, because if you see the OFDM signal, it is noise, so you can clip the signal at both the ends or at one end. So using clipping technique, and then we want to calculate the PAPR at certain BR. So in this table, it is 10 to the minus 3 and minus 5. So if you don't do any clipping and you calculate the PAPR, it is, for example, 8.94 dB in case of 10 to the minus 3 BR. But if you use clipping technique, clip at either ends or at both the ends, it gets reduced to 6 dB. So there is an advantage of 2.94 dB, which actually improves the overall performance of the system. The second method is selected mapping. Again, you get certain advantage using this. And then there is partial transmit sequence, or it is also called as PTS. So again, you see some examples. So there are a lot of techniques for reducing the PAPR. I have mentioned here 3. Some of these important techniques which have been used in literature. So with this, we have good background about OFDM, and we started with the fundamentals of OFDM, and then we discussed about how the frequency selective fading channel got converted into flat fading channel, and then we also saw using cyclic prefix, and after that we have discussed about what happens if there's a frequency offset of the subcarrier frequency, how the SINR degrades, and then also we understood about PAPR, which is the main issue in OFDM transmission, and the effect it has on the performance, and what are different PAPR techniques. So now we move to the next topic, which we will try to use this OFDM in visible light communication and understand what changes are required if I want to use OFDM in, for example, visible light communication, for indoor communication, or for outdoor communication. Thank you.